Hello, I am Priyanka Chakraborty. In my previous video, I was discussing about the PN junction diode, the depletion region, the forward and reverse biasing of diode, etc. But today, I will discussing about the VI characteristics of diode, forward and reverse characteristics, Zener diode, etc. So, let's start the session. First of all, we will discuss about the forward and reverse characteristics of junction diode. So, we know if the positive terminal of the battery is connected to the p-type semiconductor and the negative terminal of the battery is connected to the n-type semiconductor, the diode is said to be in forward bias. In forward biased PN junction diode, VF that represents the forward voltage and IF that represents the forward current. So, in case of silicon diode, if the external voltage applied on the silicon diode is less than 0.7 volt, the silicon diode allows only a small electric current. This current is considered as negligible. When the external voltage applied on the silicon diode reaches 0.7 volt, the PN junction diode starts allowing the large electric current through it. At this point, a small increase in voltage increases the electric current rapidly. The forward voltage at which the silicon diode starts allowing large electric current is called cut-in voltage or knee voltage. So we can say that the knee voltage for silicon diode is 0.7 volt. But in case of germanium diode, if the external voltage is less than 0.3 volt, the germanium diode allows only a small electric current. That current is considered as negligible. When the external voltage applied on the germanium diode reaches 0.3 volt, the germanium diode starts allowing large electric current through it. At this point, a small increase in the voltage increases the electric current rapidly. The forward voltage at which the germanium diode starts allowing the large electric current is called knee voltage. So we can say that the knee voltage for germanium diode is 0.3 volt. So knee voltage for silicon diode is 0.7 volt and the knee voltage for germanium diode is 0.3 volt. So these characteristics are the forward characteristics of silicon diode and germanium diode. Now the reverse characteristics. If the negative terminal of the battery is connected to the p-type semiconductor and the positive terminal of the battery is connected to the n-type semiconductor, the diode is said to be in reverse bias. That we all know that. In reverse bias PN junction, VR represents the reverse voltage and IR represents the reverse current. Now, if the external reverse voltage applied on the PN junction diode is increased, the free electrons from the n-type semiconductor and the holes from the p-type semiconductor are moved away from the PN junction, which increases the width of depletion region. The wide depletion region of reverse bias PN junction diode completely blocks the majority charge carrier current. However, it allows the minority charge carrier current, the free electron that is the minority carrier in the p-type semiconductor and the holes that is the minority carrier in the n-type semiconductor carry the electric current. The electric current which is carried by the minority carriers in the PN junction diode is called reverse saturation current. In n-type and p-type semiconductors, very small number of minority charge carrier is present. So, a small voltage applied on the diode pushes all the minority carriers towards the junction. Thus, further increase in the external voltage does not increase the electric current. This electric current is called reverse saturation current. So, the reverse saturation current depends on the temperature. If temperature increases, the generation of minority charge carriers increases. Hence, The reverse current increases with the increase in temperature. So the reverse saturation current is independent of the external reverse voltage. So the reverse saturation current remains constant with the increase in voltage. So if the voltage applied on the diode is increased continuously, the PN junction diode reaches to a state where junction breakdown occurs and reverse current increases rapidly. So this is the reverse characteristics of diode. So this is the combined characteristics, that is the IV characteristics of diode. This portion is the forward characteristics and this is the reverse characteristics of diode. This is the knee voltage, that is 0.3 volt for germanium and 0.7 volt for silicon. Now, when a voltage V is applied across a PN junction, the total current I flowing through the junction can be shown to be given by following equation, that is called diode equation. That is I equal to Is exponential EV by eta kBt minus 1, where Is is the reverse saturation current, E is the electron charge, Kb is the Boltzmann constant, T is the absolute temperature of the junction, and eta is a dimensionless number. The constant term eta is called emission coefficient. The value of eta lies between 1 and 2 depending on the semiconductor material. For germanium and gallium arsenide diode, eta is equal to 1, and for silicon diode, eta is approximately 2. Now, the ideal characteristics of PN junction diode. The ideal diode is a two-terminal device which completely allows the electric current without any loss under forward bias and completely blocks the electric current with infinite loss under reverse bias. Actually, ideal diode do not exist. So, the forward and reverse characteristics of ideal diode shown in this figure. If the forward voltage or positive voltage Vf applied on the diode is equal to 0 or greater than 0, the forward current If in the ideal diode increases infinitely. On the other hand, if the reverse voltage or negative voltage applied on the diode is less than 0, no forward electric current, that is If, and reverse electric current, that is IR, flows in the ideal diode. So this is the IV characteristics of an ideal diode. So the next is ZENER diode and its characteristics. A ZENER diode, also called a breakdown diode, that is a PN junction diode. A normal PN junction diode allows electric current only in forward biased condition. When forward biased voltage is applied to the PN junction diode, it allows large amount of electric current and blocks only a small amount of electric current. So, a forward biased PN junction diode offer only a small resistance to the electric current. But when reverse biased voltage is applied to the PN junction diode, it blocks large amount of electric current and allows only a small amount of electric current. So we can say that a reverse biased PN junction diode offers large resistance to the electric current. If reverse biased voltage applied to the PN junction diode is highly increased, a sudden rise in current occurs. At this point, a small increase in voltage will rapidly increases the electric current. This sudden rise in electric current causes a junction breakdown called ZENER or avalanche breakdown. The voltage at which ZENER breakdown occurs is called ZENER voltage. The sudden increase in current is called ZENER current. So, what is a ZENER diode? First, we see this symbol, circuit symbol. This is the circuit symbol of ZENER diode. A ZENER diode is a special type of device designed to operate in the ZENER breakdown region. ZENER diode acts like a normal PN junction diode under forward biased condition. When forward biased voltage is applied to the ZENER diode, it allows large amount of electric current and blocks only a small amount of electric current. ZENER diode is heavily doped than the normal PN junction diode. Hence, it has very thin depletion region. Therefore, ZENER diodes allows more electric current than the normal PN junction diode. ZENER diode allows electric current in forward direction like a normal diode, but also allows electric current in the reverse direction. If the applied reverse voltage is greater than the ZENER voltage, ZENER diode is always connected in reverse direction because it is specifically designed to work in reverse bias condition. That means it is operated in a reverse bias condition, but it acts like a normal PN junction diode under forward bias condition. Okay. So now, what is dynamic resistance? Dynamic resistance is defined as actually dynamic resistance is denoted by Rz. Rz equal to del Vz by del Iz. Actually, the breakdown curve, we see the breakdown curve in the picture. The breakdown curve should be a perfect vertical line. So, Rz has a small value ranging from a few ohms to several hundred ohms. If Vz, that is the ZENER voltage, is the operating voltage of a ZENER diode, and Iz is the corresponding ZENER current, the DC resistance of the diode is Vz by Iz. That is the static resistance. That is Vz by Iz. But the dynamic resistance denoted by Rz of the ZENER diode is given as Rz equal to del Vz by del Iz, where a change del Iz in the operating current produces a change del Vz of the operating ZENER voltage. Thus, Rz is the reciprocal of the slope of the Vi characteristics curve. In the ideal situation, Rz equal to 0, where the ZENER characteristics is parallel to the current axis. We can see that Rz equal to del Vz by del Iz. This portion is denoted by del Vz and this portion is denoted by del Iz. The change in voltage and the change in current. So this is the applications of ZENER diode. Actually, it is used as a voltage regulator, used as a switching operation in clipping and clamping circuit, and different type of protection circuit. Previously, I said that there are two types of breakdown. One is avalanche breakdown and another is ZENER breakdown. So, when a reverse bias voltage is applied to the avalanche diode, the free electrons, that is the majority carrier in the N-type semiconductor, and the holes, that is the majority carrier in P-type semiconductor, are moved away from the junction. As a result, the width of depletion region increases. Therefore, the majority carriers will not carry the electric current. However, the minority carrier experience a repulsive force from the external voltage. As a result, the magnetic carriers flow from p-type to n-type and n-type to p-type by carrying the electric current. So electric current carried by the magnetic carrier is very small. This small electric current carried by the magnetic carriers is called reverse leakage current. If the reverse bias voltage applied to the avalanche diode is further increased, the magnetic carriers will gain a large amount of energy and accelerate it to greater velocity. The free electrons moving at high speed will collide with the atoms and transfer their energy to the valence electron. The valence electrons, which gains enough energy from the high-speed electrons, will be detached from the parent atom and becomes the free electrons. These free electrons are again accelerated. When these free electrons again collide with other atoms, they knock off more electrons. Because of this continuous collision with the atoms, a large number of magnetic carriers, either free electrons or holes, are generated. This large number of free electrons carry excess current in the diode. When the reverse voltage applied to the diode continuously increases, at some point the junction breakdown or avalanche breakdown occurs. At this point, a small increase in voltage will suddenly increase the electric current. This sudden increase of electric current may permanently destroy the normal PN junction diode. However, this breakdown is called avalanche breakdown, and this process is cumulative and produce an avalanche of carriers in a very short time. That's why this mechanism is known as avalanche breakdown. And the second one is Zener breakdown. Zener breakdown occurs when the reverse bias voltage across the PN junction is sufficiently high, so that the resulting electric field at the junction exerts a large force on a bound electron to tear it out of its covalent bond. Thus, the direct rupture of covalent bonds produces a large number of electron-hole pairs, thereby increasing the reverse current. This process is known as Zener breakdown. So, there is some difference between the avalanche breakdown and Zener breakdown. For heavily doped diodes, Zener breakdown occurs at voltages below 6 volt. For lightly doped down, the breakdown voltage is greater and avalanche multiplication is predominant. Despite the two different mechanisms, breakdown diodes are commonly referred as Zener diodes. Zener breakdown occurs in a junction having a narrow depletion region. With the rise of temperature, the energy of the valence electron increases so that a lower applied voltage can pull this electron out of their covalent bond. So, the Zener breakdown voltage decreases with the increasing temperature. So, that's why the temperature coefficient of the Zener breakdown voltage is negative. On the other hand, avalanche breakdown takes place in a junction having a wide depletion region. With the rise of temperature, the crystal ion vibrate with a greater amplitude, increasing the possibility of collisions of the carriers and the crystal ions. The carriers thus have less opportunity to pick up enough energy between collisions to trigger the avalanche process. That's why we can say that the temperature coefficient of the avalanche breakdown voltage is positive. So these are the difference between avalanche breakdown and Zener breakdown. So these are some applications of PN junction diode. Okay. So that's all for today. There are some important questions from this portion. You can note this. So that's all for today. In my next video, I will discuss about the rectifier. So if you like my video, then please like and subscribe my channel. And you can also give me some suggestion to improve my videos and channels. If you want to get any idea about any other topics about electronics, please drop it into the comment box. So thank you and goodbye. Stay safe.